Alright class, today we're going to be working on Chapter 5, Section 3, Binomial Distributions. They're a bit different than probability distributions, but they're a type of probability distributions. It's a specific type that has the idea of two-ness. It's kind of a made-up word, but it gives you the idea that you only have two options when you look at a binomial distribution. There are four requirements that are needed to have a binomial probability distribution. The first is that you have a fixed number of trials. Those trials are all independent, so one does not impact the outcome of the next. The trials are classified into two categories. For example, success, failure, make, miss. The probabilities are the same for each trial, so if one trial has a 30% chance of success, the next one has a 30% chance of success, and so on. For example, rolling a die 10 times to find the number of times the number 4 occurs. Is this a binomial situation? Well, it has a fixed number of trials, 10, so it meets that requirement. The trials are independent, rolling one die and then rolling the next. That has no impact on the succeeding rolls. You do have two outcomes. It either rolls to be a 4 or a rolls not to be a 4. And the probabilities are the same for each trial, so the chance of rolling a 4 each time is 1/6. So that one does meet the probability distribution requirements for binomial. The next one, picking 10 cards from a standard deck, and quickly we see that we do have a fixed number of trials, 10 I guess, but you have many more than two outcomes, so that would not be a probability distribution. Now there's different ways to figure out the value of a binomial probability distribution. The first is using a table in the back of your book in Appendix A. So take a moment, open your book, look at Appendix A, Table A1 in the back of your book, and just stop the video for a moment until you find that. Once you have found it, we want to know the probability of, say, 7 trials, 3 successes, and the probability of success is 10%. So if you look at your table on the left-hand side, you see n. You go down and find where n is 7. And then right next to it, you'll find the number of successes, x, which is 3. And then across the top, you'll see the various probabilities. Find where p is 0.10. Find where the horizontal and vertical columns align, or I guess cross, and you'll see that the probability of getting 3 successes out of 7 trials with a probability of 10% is exactly 0.023. The next one is just a practice for you to make sure you are reading the chart correctly. N is 14, the success is 5, or 5 times out of 14, and you have a chance of 30%. What's the chance of having 5 successes in any order out of 14 tries, and each try you have a 30% chance of success? Well, if you look at your chart, you'll find that the column and the row intersect to become 0.122, so you have about a 12.2% chance of that success. The problem with this using this chart is that n only goes up to 15. So if you have more than 15 trials, this chart in the back of your book is kind of useless. And you have some limitations on p. They only give you kind of rounded percents, so you don't see that you have 53% or 47% across the top. So there are some limitations on that chart, but it is useful in some situations. Next, you see that you have a binomial probability formula. This formula will work in any situation. So I give you the formula. The probability of success x is n factorial over n minus x factorial, all times p to the x times q to the n minus x. When you look at this formula, you should recognize that the first part the n factorial over n minus x factorial is really just the same as combinations n choose x. So rather than going through all of that formula, we can use our calculator to do the combinations part, and then p to the x times q to the n minus x. On the left side, I've written out what those variables stand for. N is the number of trials, x is the number of successes, p is the probability of success, and q would be the probability of failure. So this formula works for every situation. The problem is that it's rather cumbersome, or we can say it's just kind of big and ugly, and it's not the easiest thing to use, but it will work every time for any binomial situation. So let's just practice this. Use the binomial probability formula to determine the probability with the given information. So you have 10 trials, we want to know, we want to have 7 successes, and the probability is 80%. So I'm just going to use this formula where we have combinations 10 choose 7, p is 0.8 to the 7th power, q it must be 0.2 to the 3rd power. If the probability of success is 0.8, then the probability of failure must be 0.2. Notice the order doesn't matter where I have those 7 successes. That's why we have combinations, because the order doesn't matter, but I must have 7 successes, so I have 0.8 to the 7th power. If I have 7 successes, then I must have 3 failures, and the chance of those failures would be 0.2. So if I multiply all this up, I've got combinations 10 choose 7 is 120, 0.8 to the 7th is 0.2097, and 0.2 to the 3rd is 0.008. Multiplying that, I get 0.201, and that's my probability of having 7 successes out of 10 tries, given that each try I have an 80% chance of success. Next, I'd like you to go ahead and practice the next problem using the binomial probability formula. Give that your best shot, and then I will give you the solution in a moment. But before going through the video too far, just stop the video and try that next practice problem. Alright, I hope you did that. The probability would look like this. The combinations 18 choose 3 times 0.4 to the 3rd times 0.6 to the 15th. Multiplying all that out, we can see we have 816 times 0.064 times 4.702 times 10 to the negative 4th. That product is 0.0246. So that's the probability for that binomial distribution. Alright, the next way we can find the probability of a binomial distribution is using our TI-84. This might be the most convenient way to do things. So we're going to use this, and we're going to find the probability. If you have 12 choices, the chance of 7 successes, and the probability of success for each one is 0.6. So on your TI-84, you're going to have to hit the buttons second vars, which brings up the distributions, and then toggle down to A. There you should see binomial PDF. So you'll hit that enter on your calculator. For a binomial probability distribution, the PDF is probability distribution function. You have to put the values in a particular order: n, p, and then x. So in our case, n would be 12, you'd have to put in, then 0.6, and then 7. So your calculator would look exactly like binomial PDF, parentheses 12, comma 0.6, comma 7, close parentheses. Now some of you might have a little different type of calculator. It might not ask for it in that order like that, or it might prompt you to put in those values. But in either case, it should be relatively easy to follow, and you should get 0.227. Much easier than working through the big formula. If you practice again for the probability for n is 8, x equals 3, and p is 0.2, make sure you do this on your calculator. You would have binomial PDF, parentheses 8, and then 0.2, and then 3, and you should get 0.147. Make sure you can do that on your calculator. Alright, let's look at a problem or two. Sports are an easy one to use, and I think it makes sense to use these sort of illustrations to help us see clearly what a binomial probability can do. So let's say that I can make 90% of my free throws that I shoot. What's the probability that I can make exactly 7 out of 10? Alright, on the left, if I use the table, I'm going to say n is 10, find x where it's 7, and then go over to on the right side on the top of your page, and you'll find 0.9, and you'll find where the column and the row intersect, and you will get 0.057. So that's the probability that I can make exactly 7 out of 10 if I'm a 90% shooter. But what if we just use the formula? Then I'm going to have combinations 10 choose 7, 0.9 to the 7th power, 0.1 to the 3rd power, and again, if I crunch that out, I get 0.057. If I use the TI-84, then I'm going to say binomial PDF, parentheses, 10.97, which equals again 0.057. So in all of those cases, we get the same value. Please look at them and do those each separately so you're getting enough practice for each kind. The next problem, or the next part that I would like to do, is the C part rather than B. We'll come back and pick that up at the end. The question is, what is the probability that I can make at most 7 out of 10 if I'm a 90% shooter? So again, if I use the table, I can look at the table and say I want to know the probability that x is less than or equal to 7. That would be at most 7. And I can simply add up the values that are there. 0.001, 0.011, and 0.057. There are several 0.000 plus, I believe it says, but those are so small that they just put zeros there and we don't add those on at all. If I add these up, I get 0.069. I can also do this on my TI-84, probability that x is less than 7, but now I'm going to have to use binomial CDF. That's down to the B value. Instead of using A, it's binomial CDF, and I'm going to have to say 10, 0.9, and 7 in parentheses, and I get 0.0702, a little bit higher than the other one, but for all practical purposes, it is fine. Notice it is a little bit higher because those first ones that were zeros pluses were not included in the table but are included in the TI-84. Either answer would be fine. Now let's look at B. The probability of making at least 8 out of 10. I'm going to use the table and the TI. Doing this for the binomial probability formula is just too long because I'd have to do each one of those separate and then add up all of the results. So using the table, I'm going to use the probability that x is greater than or equal to 8. That means at least 8. And I would find that I have 0.194, 0.387, and 0.349. Please look at this in your table in your Appendix A for binomial distributions. Make sure you can find each of those probabilities. And when you sum them up, you get 0.93. Now, if you used TI-84, the probability that x is greater than 8, I'm first going to have to find the binomial CDF 10.97 because the way your calculator works is from a certain number on down. I know I'm looking for a probability of 8, 9, and 10, but the calculator thinks from a certain number on down, so I'm going to have to say binomial CDF 10.97, which is 0.0702. But I'm not wanting 7 on down, I'm wanting 8 on up through 10. So now I'm going to have to subtract what I have, 0.0702, from 1 and get a 0.93. Specifically, it would be 0.9289 off your calculator, but we can see that that's very close to the table that we have, the answer from the table that we've been given as well. That should conclude what we have. The next part, or the last couple of problems, we will work on those in class to begin our next session. You should be able to work through your assignment now in class the following day.